Good day po, sir. We are Group 11 from AM2, and this is our final data science project. So the first part is, of course, data gathering. For data gathering, we sought a dataset that achieves equilibrium between simplicity and complexity, ensuring its extensive and impartial characteristics. Following given instructions, we explored various sources such as Kaggle and ultimately opted for a metropolitan and micropolitan statistical area, Mmsa, dataset found on GitHub. Our toolkit comprised of pandas for efficient data manipulation, NumPy for numerical operations, and matplotlib for plotting V-graphs and such. Additionally, we also incorporated Seaborn for statistical data visualization. Following the import of the necessary module, we accessed an MMSA dataset from a CSV file. MMSA dataset CSV is a file using pdread to create the COVID US pandas data frame. So the dataset that we got um, is based on the different factors of the hospitals in the US during the pandemic. So there's total percent at risk, high risk per ICU bed, high risk per hospital, ICU beds, hospitals, and the total at risk. So I explained the first codes. We now go to data cleansing. In the data cleansing phase of our project, we are meticulously improving the quality and relevance of the COVID US data frame to ensure accuracy and alignment with our project objectives. Initially, we access column names to comprehensively review available columns and identify elements that do not significantly contribute to our analytical goals. After careful evaluation, ICU beds is identified as a candidate for removal in line with our strategic focus on extracting essential information. The subsequent removal of the ICU beds column streamlines the dataset, providing a more focused foundation for insights. Visual confirmation is obtained by examining the first few rows of the updated COVID US data frame. Finally, descriptive statistics are generated to gain key insights into central tendencies and variability, enhancing our understanding of the refined dataset. So, as a group, we came to the decision that the ICU beds weren't of much importance to um, the questions that we chose to answer in this dataset.
In this line calls the info method on the data frame copied US, which prints a concise summary of the data frame, including its index D-type, column D-types, non-null values, and memory usage. This line sorts the data frame COVID US by the column total percent at risk in ascending order and assigns the sorted data frame to the variable total percent at risk. This line prints the first few rows of the data frame total percent at risk. Note that it should be a total print instead of print. This line sorts the data frame COVID US by the column high risk per hospital in ascending order and assign the sorted data frame to the variable high risk per hospital. This line prints the first few rows of the data frame high risk per hospital. Similar to line 3, it should be print This line sorts the data frame COVID US by the column high risk per ICU bed in ascending order and assign the sorted data frame to the variable high risk per ICU bed. This line prints the first few rows of the data frame high-risk ICU beds, similar to line 3 and 5, it should be print. This line sorts the data frame COVID US by the column hospital in ascending orders and assigns the sorted data frame to the variable hospitals. This line prints the first few rows of the data frame hospitals, similar to the line 3, 5, and 7. It should be print hospitals. This line computes the correlation matrix for the data frame COVID US using the core method, which calculates pairwise correlation of columns, including NA or null values. This line prints the correlation matrix computed in the previous step. This line sorts the correlation value related to the column high risk per hospital in descending orders and assign the result of the variable significant variables. This line prints the correlation value with respect to high risk per hospital. This line defines a list of selected features. This line computes descriptive statistic for the selected features and assign the result to the variable selected feature stats. This line prints the descriptive statistic for the selected features. These remaining lines are plotting commands using libraries like matplotlib and Seaborn to visualize various aspects of the data. These commands create bar plots, scatter plots, set titles and labels, and display the plots.
The next phase is called the data modeling phase. The data modeling phase is a comprehensive process for predicting COVID-19 related data using the random forest regressor model. It begins by importing essential modules from scikit-learn and pandas, followed by data inspection, feature definition, and target specification. After splitting the data into training and testing sets, it combines them into separate data frames for analysis. The code proceeds to scale the features using standard scaler, then trains a random forest regressor model with a scaled training data. Predictions are generated and evaluated using mean squared error, also known as MSE, visualizations including a scatter plot comparing actual and predicted values, and a bar plot illustrating feature importances, enhance model understanding. For the first step, import modules and classes from scikit-learn and pandas for machine learning tasks. Then, display the first few rows of COVID_US data frame to inspect the data. This is followed by defining the list, features, containing the names of specific columns in the dataset. also defining the target variable. Printing the column names of the COVID_US data frame to identify the available features comes next. Extracting the specified features and target variable from the COVID_US data frame and splitting the dataset into training and testing sets for features and target variable. The next is combining the training features and target variable into a new data frame called train_df. Similarly, combining the testing features and target variable into a new data frame called test_df. This is followed by printing the first few rows of the training dataset for inspection, the first few rows of the testing dataset for inspection as well, also the count of missing values in the training set for each column, and the missing values in the testing set for each column as well. This is followed by creating a new figure with a specified size for subsequent visualizations, creating a standard scalar instance for feature scaling, scaling the training features using the fitted scalar, scaling the testing features using the same scalar, and creating a random forest regressor model with a specified random state. The next is fitting the random forest regressor model with the scaled training features and corresponding target variable. This is followed by generating predictions using the trained random forest regressor model on the scaled testing features. The next is calculating and printing the mean squared error, also known as MSE, between the actual target values and the predicted values. This is followed by creating a scatter plot to visualize the relationship between actual and predicted values, adding labels to the X and Y axis, setting the title of the plot, and displaying the plot. The next is to extract the feature importances from the trained random forest regressor model. Next is getting the names of the features and sorting the indices of feature importances in descending order. The next is creating a bar plot to visualize feature importances, plotting the bars with corresponding importances, setting x-axis ticks and labels with rotated text for better visibility, setting the title of the plot, and displaying the plot itself. That would be all for the data modeling phase.
For evaluation. After a careful evaluation, EcoBeds was identified as a candidate for removal. With our strategic focus on extraction assumption, when removed, EcoBeds more focused foundation for insights. Visual confirmation was obtained by examining the few rows of the updated COVID_US data frame. Finally, descriptive statistics were generated to gain key insights into central tendencies and variability, enhancing our understanding of the refined datasets. The three questions in the EDA is answered here. The first one is risk percentage in different MMSA. The risk percentage in different metropolitan statistic area or MMSAs varies. For example, the total percentage at risk in San Juan, Carolina, Kanguas, PR is 52.88%, while in Manhattan, KS it's 42.29%. This suggests that the risk percentage can change significantly depending on the MSSA. Correlation. Next is correlation between high risk per ICU bed and high risk per hospital. From the data provided, it's not immediately clear if the direct correlation between high risk per ICU bed and high risk per hospital. To determine, you need to calculate correlation coefficient between these two variables. Pattern in this total number of people is at risk in different city and in town areas. Total number of people at risk within the different city and area. The United States also varies. For instance, the total at risk in San Juan, Carolina, Canvas PR is 9237225.203, which in Manhattan is 35,918.79. This suggests that the total number of people at risk can differ greatly depending on the area. In this line, import the necessary function from a scalar matrix. Next line, calculate the mean absolute error, MAE, between the actual target values and the predicted values. Next is print the calculated MAE. And here you can see the result. Next is calculate residuals. Create figure. In this line, create figure. Next is scatter plot of predicted values versus residuals. Next is set labels and titles. In this one, you can see predicted values, residuals, and residual analysis. And last in the cell is show plot. As you can see, here is the result. Another one, another cell is import cross-val score from a scalar model selection. Next line is perform cross-validation on a random forest model. Next is calculate root mean square error RMSE from cross-validation. This line print cross-validated mean square error. This line print mean RSE across folds. Here you can see the result. And the last cell, predict on the holdout set. Next is calculate mean square error for the holdout set. And the last line, print mean square error for the holdout set. That's all. Thank you.